let me start the recording. Okay, great. So I have some announcement to make before we continue. We start with Q&A 8. So as you probably already know, problem set 1 results are now available, and the details is on the blackboard. So you want to check the solution is there. If you after checking the solution, if you still have questions, you are welcome to attend. The viewing session that I schedule. Problem set 2 is scheduled on next Thursday at 4 p.m. So it's going to be the similar style to problem set 1 that you have 24 hours. More details on problem set 2 will be posted on Blackboard sometime later in the week. It would cover lecture 5 to lecture 8, including the Q&A sessions and the tutorials. And because the problem set 2 will start on Thursday, so the solution for the tutorial 8, so I will make the solution for tutorial 8 available on the next Wednesday, so like a few days earlier, so at least you have 1 or 2 days to go through the solution if you need to. And also you should catch up with the tutorial sessions of the next week, just to help on top of the written tutorial solution. Okay, great. So given that you have had a break, hopefully a nice one, the good one last week, and I also hope that you have some spare time to catch up with the lecture 8 recording. So because this is somewhat might be a quite new topic, so to most of you, which is about when we introduce risk and uncertainty into the consumer theory, and see how we can come up or how we can use a certain theory to try to predict or explain the behavior or what kind of options that this consumer would choose. Okay, so let's start with I just want to this part is new. It's not included in the lecture recording, but I find that it actually is a fundamental concept that you actually need to really understand it very clearly in order to be able to do the rest of the analysis in terms of expected utility theory. So for the expected utility theory, we in this level we are dealing mainly about mutually exclusive events. So mutually exclusive events are the events that can happen at the same time, right? So if you are a girl, you cannot be a boy. So those are mutually exclusive events. So we ignore, the birth gender, not that that you change your gender afterwards, or you want to define yourself as not the binary gender. So we don't deal with that. We just said, okay, what is your birth gender, right? It's either boy or girl. That's it. You cannot be anything else, right? And those are the example of mutually exclusive events. Or today, like for example, in Brisbane, is at the moment it stops raining, at least where I am at the moment, but it's been raining kind of sprinkle on and off the whole morning. So you can have an event in which at the moment it rains or it doesn't rain, right? You cannot have the event in which it rains and it doesn't rain at the same time. It's just not going to happen. Another property is about the mutually exclusive events, that if we consider all n mutually exclusive events, right? Like something happen, it doesn't have to be only 2 events. It could be like 3, 4 possible events, right? But they are exclusive. So, and each event could occur with the probability p sub I. So let's say the event 1 could happen with the probability P1. Event 2 could happen with the probability P2, where event 1 and event 2 are mutually exclusive. And then event 3 can happen with the probability P3, right? So when we combine, we sum all the probability of each mutually exclusive events together, it must sum up equal to 1. That's very simple, just makes sense, right? So let's look at the example. Find the mutually exclusive events of tossing a dice once. When you toss a dice once, what could be the possible events that could happen when you toss a dice once? Could be that the dice either turn 1, 2, 3, 4, 5, or 6, right? So those are mutually exclusive events. So there are 6 possible events. 1, 2, 3, 4, 5, and 6, right? That's it. It cannot be anything else. Either it turns up 1, 2, 3, 4, 5, or 6. And what is the probability of this event to occur? 1/6, right? That is a probability. What is the probability of these 2 events to happen? It cannot happen together. Okay, let me phrase it this way. What is the probability that tossing a dice once would turn the value 2 or the value 3, right? So it can either turn up 2 or 3, but what is the probability that you're gonna get either 2 or 3? The probability would be 1/6 plus 1/6, right? So the total, the probability would be 1/3, right? Like you can say that the 1/3 of the whole probability that it turns out like something else. Okay. Find the mutually exclusive events of tossing a dice twice. Now, tossing a dice twice, then you can think, okay, so the first one, there's going to be what? So many possibilities, right? You're going to have 1, 1, 1, 2, right? 1, 3. So the first one turn 1, the second one, the second time turn 1, also turn 1. First one turn 1, the second time turn 2, and so on, right? So you have so many 1, 6, and then the first one turn 2, and the second one turn 1, 2, 2, and so on. So you get so many all the way to 6, 6, right? So those are the mutually exclusive events of tossing a dice twice. Okay. Consider the mutually exclusive events A, B, C, and D. So now we have 4 possible events, mutually exclusive events. Event A occurs 25 times, B 50 times, C 75 times, D 100 times. Find the probability that event A can occur. How much is it? What is the probability? So you can either have A, B, C, or D, right? So the probability that A would happen is 25 times out of all of these times, right? So we know that the total is 25 plus 50 is 75, plus 75, 150, plus 100 is 250, right? So the probability that the event A occurs will be 25 out of 250 times. Okay. And for B, that will be 50 out of 250. For C, 75 out of 250. And for D is 100 out of 250. Or you can take 1 less PA plus PB plus PC, right? Because you know that all of these have to sum up equal to 1. So you don't actually necessarily need to know this. As long as you know the total, then you can actually get the probability of the last event, that is 1 less the summation of all the other probability, right? So you get 1 less this plus this plus this, right? Or which supposed to be equal to 100 over 250. Okay, easy peasy. Now let's look at something more like a story. Let's say I have Joanne. She is on her way to deposit her money into a bank. Okay, and what happened is she could possibly get robbed on the way with the probability equal to P. Identify all the mutually exclusive events for Joanne for her trip to a bank. So what could those be? So they are, when she's on the way to the bank, they are the events that could happen. She either get robbed or she travels safely, right? So she either being robbed, so that is one possible event, and another mutually exclusive event is she is actually safe. And what is the probability for this event? And what is the probability for this event? So there are no other events, right? Only 2. In this particular example, there are only 2 possible events, either being robbed or being safe. Since the probability of being robbed is equal to P, right? So P is between 0 and 1, okay? So she might get this event with the probability P, and being safe with the probability 1 minus P, right? Because there's only 2 events. So that's how we identify the probability associated to each event, possible event. So probably for each event. Now, suppose that Joanne split her money in half to diversify the risk of being robbed all in one go, and instead take 2 trips to the bank, right? So each trip would carry half of the money. Just assume that the probability of being robbed is independent for each trip and remains constant. That means it stays P. Doesn't matter if it's trip 1 or trip 2. The chance of being robbed is P, and also it doesn't depend on whether or not in trip 1 you are being robbed or not. This chance of being robbed in either period, in either trip, is stay constant P. Identify all the mutually exclusive events and the associated probabilities, right? So I find that maybe the easiest way to look at or identify the events is actually looking at the tree, like looking at the kind of make like a direction of how the story works, right? So we start with, okay, we start with Joanne, right? Joanne could either be robbed in trip 1, right? Or being safe, right? There are 2 possible events. So I call it, this is trip 1. Trip 1, there are 2 possible events, robbed or safe. So if she's robbed, she is robbed with probability P, and safe with the probability 1 less P. Then we are dealing with 2 trips. In the second trip, right? Regardless of trip 1, because in one trip she would carry only half of the money, right? In the second trip, regardless she's being robbed in the first trip or not, right? She might also being robbed again, or being safe in the second trip, right? I call this trip 2, right? And you do the same. If she's being safe in the first trip, she might be robbed in the second trip or being safe in the second trip, right? And the probability, so now the probability would be P, still P, 1 less P, because it's independent to whether or not which trip she is taking, right? Okay, so when you write here, you can see that it's more clear about more clear in what could be the possible events in this situation. She either being robbed in the first trip and the second trip, or robbed in the first trip but safe in the second trip, or safe in the first trip and robbed in the second trip, or safe in both trips, right? So there are how many possible events, mutually exclusive events? There are actually 4, right? Rob, safe, safe, rob, safe, safe. So there are 4, right? Which is, if you are dealing with only 1 trip, there's going to be only 2. But now you're dealing with 2 trips, so there are 4 possible scenarios that could happen. So we have, then we're gonna get I call it rob, right? Rob in the first trip, safe in the second trip. Safe, rob, or rob. Okay, you can see that this and this are not the same, right? This means that being robbed the first trip, but not the second one. But this one, it means she's being robbed the first trip. Oh no, she's being robbed the second trip, but not the first trip. Oh, the last one has to be safe. I'm sorry. This should be safe, right? Okay, so what about the probability now? Now we identify all the possible mutually exclusive events for this case, right? Of taking the money in 2 trips. So what about probability? We need to know how much is the probability for this event. How much is it? Rob and drop. What is the probability? How much?
Is it P times P?
Yes, it's gonna be P times P, right? Because you're going to this way. Drop will be P times P. What about safe in the first trip and drop in the second trip? Safe in the first trip and being robbed in the second trip, that would be 1 less P times P, right? So we know that it is the probability. So that there will be P times P for this. This one gonna be P times 1 less P. This one would be 1 less P times P. This one would be 1 less P times 1 less P or 1 less P squared, right? And that's all. So we know, we identify all the possible events, and we now identify the probability associated to each event. And all of this, when you sum them all together, it has to be equal to 1, right? Okay. So all good. No question about this? This is clear? Okay. So next, now you understand this mutually exclusive event, right? So now I'm just gonna take you to how we actually going to illustrate, those possible outcomes, the outcomes associated to each event in the, in the 2-dimensional diagram. So let's say that we're gonna consider only two state, 2 possible events. So to make your life easier, to just simplify just 2 events. So since they are mutually exclusive, like we have state 1 and state 2, right? Then they do not overlap to one another, because obviously they either state 1 happens or state 2, but not all together, right? And let's say that state 1 occurs with the probability P, right? Therefore, the state 2 would occur with the probability 1 minus P, right? And when this event happens, what we care about in economics agent, in the consumer, is we care about if this state 1 happen, what is the outcome in terms of wealth, right? I'm gonna call it wealth. Call it wealth 1. And if instead we end up with state 2, if state 2 occurs with the probability 1 minus p, what would happen to the wealth in state 2, right? And we're gonna say that, okay, now with state 1, if state 1 happens, this is going to be the outcome, you know, the wealth associated to this event, right, with the probability p, okay? And if instead event 2 occurs, this is going to be the outcome associated to the state 2 given the probability 1 less p. Let me put it in this 2-dimensional diagram. Okay, we call this C1, which is, you can call it wealth 1, the bill 1, the same thing. So C1 just like consumption, you know, consumption value or something like that, or wealth. It is a consumption in state 2. Now, state 1 and state 2, they are mutually exclusive. Okay, don't confuse it with X and Y that we learn in consumption bundle when, oh, you consume X and Y together, right? That's how you have your utility function, X, Y equal to whatever, like X to the power 1/2 times Y to the power 1/2. Like in previously, that is how we deal with the utility function and indifference curve based on X and Y, that you consume it together. However, in this lecture 8, in the uncertainty, this C1 here and C2 here, you do not consume them together. You understand that this C1, because they cannot happen at the same time, right? If you consume C1, you cannot consume C2 and vice versa, okay? So this is like different, the main difference. Now, so when you look at this, just like have to think of it in a different mindset. Okay, but I think that it's clear now that you can clearly see that C1 and C2, either you consume, for example, if I pick that bundle, it's not actually bundle, not bundle anymore, point A, let's say at point A, right? At point A, 3, 1. What does it mean? At point A, 3, 1, right? 3 here and 1 here. What it means is that if the event 1 occurs, my wealth, my consumption is equal to 3. And if the state 2 or event 2 occurs, my consumption or my wealth level is equal to 1. Okay, that's it. That's what it means. You don't consume them together, okay? So point C, right? That means that, right? If state 1 occurs, if event 1 occurs, I get 0. If instead event 2 occurs, I get 3. Now, along the 45-degree lines, we know that at the 45-degree lines, C1 must be equal to C2, right? Any points here, C1 is equal to C2. What does it mean is if I pick point D, 2, 2. If I end up with state 1, I get 2. If I end up with state 2, I also get 2. That means that it doesn't matter either state 1 or state 2 that occurs, I end up with the same wealth, the same level of consumption. That's why it's also called a certainty line. Even though you know that it's not certainty, but it's certainty in the way that you know what your outcome is going to be, what your wealth is going to be. In this case, you know for sure that doesn't matter if it rains or it doesn't rain, right? You will end up with the same value of wealth, right? So any points along here would give you a certainty amount of wealth, but it doesn't mean that you know for sure which one you're gonna get. But you don't know for sure that you will end up with state 1 or state 2. What you know for sure is that you will end up with the same amount of wealth, right? That is a certainty in the wealth wise. So it's certain that you know for sure what the wealth is going to be, but you don't know for sure which events you're gonna get, right? Now, if you think about, for example, you can think about buying insurance, right? buy insurance actually give you that kind of certainty. You don't know that. Let's say you buy a car insurance. Of course, you don't know that you're going to have an accident or you're not going to have an accident, right? There are two possibilities. There are two possible events. Either you have an accident or you do not have an accident. But let's say that if you buy an insurance that it gives you the full coverage, right? That means that you know for sure that it doesn't matter. You have an accident, you are not having an accident, you will end up with the same amount of wealth because when you buy full insurance, that means that in the case of an accident, if the accident costs you $5,000, right? But because you buy the full insurance, then the insurance is gonna pay you out for exactly $5,000. So you know for sure that at the end of the day, you will end up with with that amount, regardless of you have an accident or not, right? So, and that is the the application of the 45-degree lines, when you will have a certainty in terms of wealth. Okay, so everyone's clear about this, about this graphical representation of this state contingency consumption bundle, in that sense, not really a bundle. Okay, so let's move on to the utility function. So because C1 and C2, right, these are state contingent consumption which are mutually exclusive, right? You either consume C1 or you consume C2, right? But because there is this certain probability that you will end up with C1 or you will end up with C2. We define this, what we call the expected utility function, or the von Neumann-Morgenstern VNM utility function, as the probability that state 1 occurs multiplied by the utility value of the wealth from state 1 plus the probability that state 2 will occur multiplied by the utility value of wealth if you are in the state 2. Okay, so don't get confused between expected wealth. So this is, I can call it expected utility. I can put E to make it very clear that expected utility. So either you put a capital U, you use capital U, that means it is the expected utility. This is a small u. Okay, so that just to differentiate between expected utility versus just the utility function. Or you can put expected u. Don't get confused between expected u and expected wealth. They may look similar but they are not interchangeable. And I find that at least 20 or 30% of the students, based on the problem set that I marked in summer, so in the previous semester, about 20 to 30% of the students, when I asked you to compute expected utility, you actually give me expected wealth. You know what the difference between expected wealth and expected utility, or can call it expected C. Expected C or expected wealth would be pi, the probability that you will have C1 multiplied by C1 plus 1 minus pi, the probability that, which is the probability that state 2 going to happen, multiplied by the consumption value of state 2. You see the difference? These are not the same. Okay, so for expected utility, remember that you cannot just multiply pi directly with the wealth value or just the consumption value. You need to actually insert the utility function first. Okay, whatever the utility function is, Of course, if I said my utility function is equal to C, then it's very clear that this one would equal to this one, right? Expected value would equal to expected utility if my utility function is equal to C, but most likely it's not. Right? Let's say if it's equal to square root C, for example, right? Then you need to, then that means that this value would be pi times C1 square root C1 plus 1 less pi times square root C2, okay? That is the expected utility. But if I ask you to compute the expected value, then you do this. Okay, you don't need to, to put in the utility function first. You just take whatever the value multiplied, that's the expected value. Okay. So I hope that I don't see this mistake, in the problem set or in the exam. As I make it very clear, or hopefully reduce the number of students doing this mistake. Okay, so now we are here at the expected utility function, right? So probability multiplied by utility value, okay? Therefore, if you take the partial derivatives of this expected utility function with respect to C1, you will get that, right? And MU2 would be this. As you can see that MU1 doesn't depend on C2, right? Obviously, because event 1 and event 2 are mutually exclusive. So MU1 will not depend on C2 and vice versa. Okay. So, okay. So essentially, utilities from the two states are perfect substitutes with each other. So you can think of it as like either when one happens, you consume either one or another, but not two together, right? It's a substitute. You either consume state 1 or you consume state 2. And now what you see here is actually if I divided MU1 by MU2 and I put the negative sign in front, that looks like MRS XY or MRS C1, C2, right? Right? It's like marginal rate of substitution is equal to negative MU1 over MU2. And that's what we're going to get. The thing is now, instead of our utility function as it is, this is our utility function. So our MRS, which is the slope, now you can actually get kind of an indifference curve, right? Based on this utility, the capital utility, the big U function, you can get the indifference curve. And also the marginal rate of substitution, which is the slope of that indifference curve, just based on these two values. Okay. Okay, so the next concept, expected utility maximizer, right? Now, a consumer would actually maximize the expected utility when he or she faces the uncertainty, right? Now, she's just not gonna maximize utility. You only maximize utility if you have a certainty. If it's not certain, that means there are possibility that you might end up with state 1 or state 2. You're actually going to maximize the expected utility instead, because you don't know what you're going to get. Either you're going to get C1 or you're going to get C2. What do? You just maximize that expected utility, which is maximize this function instead, right? And now you think about it. Okay, now you maximize this function. What does it get you? Okay, you would need, okay, I maximize this function with respect to budget constraint. What is going to be my budget constraint? We're going to talk about that later. But what you know is that what you want is you want to achieve the maximum value of this, right? Whatever that is, then that is what you want to get. So an expected utility maximizer will choose the option with the greatest value of his or her expected utility. And we will talk about option later. Consider options A and B. Now, this is not just the bundle A and B. Remember now, A and B here is just option A, which is the amount of C1, C2, right? At point A. And option B is a different amount of C1, C2 at point B. Okay. So option A and option B, this option may have the same or different mutually exclusive events from option B. And the probability might be different as well. Like option A and option B, like, doesn't necessarily have to have the same events, the same possible events, or doesn't necessarily have to have the same probability associated to each event. It could be like completely different events. But what we care about is actually the wealth, the wealth that each event is going to happen, and the probability that that we're gonna get to each, but we would get each possible events, and then we could compute the expected utility, right? So option A is weakly preferred to option B if and only if, when you compute the expected utility value for option A, has to be at least as much as the expected utility value of option B. That means you are weakly prefer A to B. That's it, like very simple, right? So in the past, you would say that, okay, I weakly prefer bundle A to the bundle B, right? Or I weakly prefer, let's say, XA, YA. If it's a certainty case, right? XA, YA is weakly preferred to XB, YB. If and only if, right? U of XA, YA has to be greater or equal to U of XB, YB, right? So similar concept. Here we use expected utility instead. So instead of just utility value, we use expected, and the expected must include the probability for each event, right? Okay, so we have this, and then so to find which options would be best for this expected utility maximizer is first, so step one, identify all the mutually exclusive outcome, C1, C2, maybe there might be like 5 possible outcomes, like 5 possible events. So each event will have a certain outcomes happening with some probability, right? Doesn't have to be 2, it could be 3, 4, 5, 6, or 10. But identify all the mutually exclusive events and the associated probabilities of option A. Do the same for option B, right? Just repeated it. Doesn't have to be the same kind of events, could be different, as long as you know the outcome associated to each event and the probability for each event. Then you compute expected utility of A, which is pretty much that P1 UC1 plus P2 UC2 all the way, whatever, how many events option A has, right? Do the same for option B. So N and M doesn't have to be the same numbers, right? Maybe you may have only 2 events here, maybe 3 events here. What about, can we compare the 2 options in which one option actually have only 1 possible event, or is actually there is no uncertainty? Like for example, if I have option A that either it rains or it doesn't rain, and compared to option B when I just say that, okay, there is only 1 possible event, which is the probability 100%. Yes, you still can compare those, even so one is uncertainty, another one is certainty. How you do it? Well, that means that expected utility of the certainty option would equal to, there is only 1 case, right? That would be Pj, which is equal to 1 times utility value of the outcome of that certainty. That's it. And you still can compare it, right? So then you compute this expected utility across these two options. And then choose which one has a greater value, right? This consumer weakly prefer option A to B if and only if this computed value is greater or equal to this value. So it doesn't necessarily mean that you will always choose the option with certainty, right? So it depends on this. Actually, it doesn't depend on that certainty. It depends on the expected utility value. Okay, so that's the 3 steps that you need you should follow to choose the right option when we are dealing with the uncertainty. Now, so it's just like an expectation. Yes, so that is the expectation. So Joanne, again, now we go back to the Joanne situation, but instead now I give you the utility function. Now Joanne has a utility function, okay? And Joanne put only $1 in her bank account, but store all her other cash, $100,000 at home. Okay, Joanne is on her way to deposit $100,000 into a bank. Okay, she could get robbed on the way with probably 20%. Now I give you the particular value of P. Now P is equal to 0.2. Suppose instead of carrying out the cash in one go, Joanne can split her cash in 2 halves and make 2 trips to the bank. The probability of being robbed on each trip is still 20% and is independent across trips. If she is robbed on a trip, she loses all the cash. Not he. She is carrying on that trip, but not the cash on the other trip, unless she also gets robbed on the other trip. Okay. Would Joanne prefer to make 1 trip or 2 trips? Right. So now there are 2 options here. Option 1, or I call it option A, is to make 1 trip. And the option B is to make 2 trips. Now you have to choose. Would you prefer option A, or would Joanne prefer option A or option B? Right? So for option A, 1 trip, option B, 2 trips, what do you have to do? Well, back to this. First, identify all the mutually exclusive outcomes and the probability of each option. Compute expected utility, and then compare those values, and then you will choose whatever that have a higher expected utility value. So we start with option A. So what I probably would like to do is maybe cut this in half. Okay, and I call this option A. Right, 1 trip. Versus option B, 2 trips. Okay, you want to remember, first find the mutually exclusive events for each option. So in option A, with 1 trip, we have learned previously that with 1 trip, right? If you have only 1 trip, then she either get robbed or saved, right? Now probability of being robbed is 20%. That means the probability of being saved would be 0.8. Yeah. So, and what is the wealth or the outcome? So next, you know the events, and you need to know the probability, and you need to know the wealth value associated to each outcome. So the wealth value here is if she is robbed, right? Only 1 trip, that means she lost all of $100,000 that she carried. So that means that what is her wealth if she get robbed? The wealth is $1. Don't forget the $1 that she already has in the bank. Okay, it's not completely zero, right? Because she still have she have $1 in the bank. If it's safe, if she didn't get robbed, it is safe, then she would have this wealth. So this is her CR, this is her CS, right? Two possible wells. So we have wells, we know wells for each event and also the probability associated to each event. You can now, and you also, what else do you know? You also know her utility function, or not the well utility function. So her UW is equal to log W, right? So you can compute the expected utilities. I call it EUA, right? Expected utility of option A is equal to 0.2 times log of 1 plus 0.8 times log of 100,001. Don't forget that you need to insert the utility function here. It doesn't equal to 0.2 times 1 plus 0.8 times 100,001. Okay, that is expected wells, but not expected utility. Okay, so expected utility would be 0.2 times log of 1 plus 0.8 times log of 100,001. Okay. And that is equal to 9.21. Okay. So you get UA, EUA. Can you do EUB? Okay, I give you 5 minutes to do a EUB. I do the easy one for you. So with 2 trips, what are the possible events? We already did that in with 2 trips, there will be 4 possible events, right? And you know what is the possible, what are the probabilities for each event. You should be able to find EUB. I give you 5 minutes, okay? To do this. Okay, did you guys finish? Yep. So 2 trips or 1 trip? 2 or 1? You can type 2 trips or 1 trip. 2 trips. Everyone agree 2 trips? Someone even write the value of expected utility. Okay, so yes, the answer is 2 trips. So let's work on this together. We know that there are 4 possible events, right? Rob, save, rob, or save, right? And each, so rob probability would be 0.2 times 0.2, right? Rob save would be 0.2 times 0.8. Save rob 0.8 times 0.2. Save 0.8 times 0.8. And the wealth, if you are robbed in both trips, you end up with $1 in the bank, right? The safe deposit that you have, robbed and saved. So you split the money in half. So you split 100,000 in half. So that means that each trip you carry $50,000. In this case, since the first trip is robbed, so you only have $50,000 saved plus another dollar on the bank account. So the wealth in this scenario is 50,001, right? Same here, 50,001. This one gonna be all safe, right? Okay. Do not forget this $1 in the bank. Okay. Most students forget about this. Just try to not forget about that. Okay. But if you do, it doesn't really matter much. I mean, but of course it's not going to be the perfect answer. And now next you compute the expected utility of this option B, carrying 2 trips, right? That would be 0.2 square times log of 1, log, plus 0.2 times 0.8 twice, times log of 50,001, right? Because these 2 numbers are the same, so it can just combine them together, right? Because it's the same wealth, times log of 50,001, or you can do it separately, it doesn't matter, it's gonna give you the same answer anyway, plus 0.8 square times log of 100,001. So 0.2 square times log of 1 plus 2 times 0.2 times 0.8 times log of 50,001 plus 0.8 square times log of 100,001, right? And that should be 11. Does anyone admit that you forget to add $1? Raise your hand. This is a problem set in summer last semester, and I would say about 70% of the students forget the $1 in the bank. So of course, I'm not going to ask the same question in this problem set, but just that you have to be careful when considering the wealth associated to each event. Okay, so this is 11.8, 82, which is greater than 9.21. Therefore, we choose option 2 or option B, 2 trips, right? Because Joanne is an expected utility maximizer, so she would choose the option with the highest level of, with the greatest level of expected utility value. Okay. Now again, let's change the question a little bit. Suppose now that Joanne can only make 1 trip to the bank, okay? And we have a transport company, Mali Inc., offers to transport Joanne's cash to the bank for her, Mali Inc. would guarantee that Joanne's cash arrives safely at the bank, but charges a fee in return. Find the highest amount of fee that Mali Inc. can charge Joanne. What do you think that we should set up this question? So I didn't ask you, should Joanne use the service or not, right? So I'm not asking you about choosing option A against option B. I'm asking you instead that finding the highest amount of fee that Mali Inc. can charge Joanne. Then how do we do it? So that Joanne is still willing to use its service. Now we are comparing two options here. Option A is Joanne make one trip to the bank by herself. That option A, right? So pretty much you already know what the expected utility for option A is like, right? And now option B is that she use this service, like cash transportation service. So the hint is that Joanne is still willing to use this service. That means, what does it mean? That she strictly or she is weakly prefer this service to carrying the cash herself, right? So option A, do it herself. Option B, use the service, right? But what we know is that she is willing to use the service. That means that expected utility for the option B has to be greater or equal to the expected utility of option A. So instead, it's kind of like go a little bit backward. Instead of asking you like a direct, straightforward question, now it's going backward, right? Now I just tell you what it means, that you just have to decode the hints here. So what it just gives you, it just tells you that, oh, she used the service. That means that B is weakly preferred to A, right? This option B must be strictly weakly preferred to A. That's why she would use this service. So we know that now we have option A and option B. To option A and option B still okay, but with option A you already know what the answer is, right? So you know the value. So option A, one trip by herself, right? Option B, use Mali service. Okay, so with option A, you already know that expected utility of option A is equal to 9.21 from the previous question. Now with option B, you don't know what it is. You just know that this is EUB, right? Equal to some numbers, you don't know. But that's not what the question asks you to find the fee, the highest amount of fee that Mali Inc. can charge Joanne, right? Okay, but what you know is this one has to be greater or equal to EUB, has to be greater or equal to EUA. Okay, and EUB has to be how we find EUB. EUB is equal to P1 times log of so it is actually summation of PI. We need to find first how many possible mutually exclusive events for option B is multiplied by log of WI, right? So with option B, we know that there is only one possible event, which is that it doesn't matter, you end up with $100,001 in the bank, right? That is the only thing that could happen. Like, doesn't matter if it gets dropped or not, but at the end of the day, you will have, if you use this service, you will only have one certainty, which is the probability of 100% that you end up with 100,001, right? But so this is probably 1 times log of 100,001 in your bank. But remember, to use this service, you have to pay the fee. So the total wealth that you end up with would be 100,001 less the fee that you have to pay. Okay, so this is the wealth. So for sure, this is what you're gonna end up with if you use the service. Now you can say that you can solve for f, right? Whatever that f is, because we know that this number has to be greater or equal to 9.21. So 9.21 has to be less than or equal to log of 100,001 minus f. So I take exponential in both sides. Right, and I can do that without changing the sign because it is an increasing transformation. So I take the exponential on both sides, then I get this. Therefore, f has to be less than or equal to this value, which is what is it? Which is 90,004.4. And that's the answer. Any question for this? All good? Okay. So that is a numerical example of how you can apply the expected utility function to to choose the best option when you are comparing between the two options, which could be risky. Both of them could be risky options, or one could be risky, another one can be certainty. Doesn't matter, right? And you don't, and as you can see that in this case, for example, you don't necessarily need to have the same event, the same kind of event, right? Doesn't matter. You can always compare by just computing expected utility value between each options. So the main thing is just make sure that you identify correctly all the mutually exclusive events and the wealth for each of the events, as well as the correct probability for each event. And then when you compute the expected utility, do not forget to insert the utility function in that computation of expected utility. That's why we call expected utility. I know I repeated myself over and over again because it's just a common mistake, so common that I need to emphasize a lot, so you don't do that mistake in the problem set. Okay, next. So when we're dealing with just a utility function with a certainty, we know that, okay, if u, x, y represent a preference, right? And we know that, okay, I can, put the increasing transformation, strictly increasing transformation of the utility function of x, y, and that would also represent the same preference. We learned that in the previous lecture. Now with the expected utility function, we can somehow transform the function but in just only a certain way. Not any increasing transformation would work for this because we are dealing with this probability, right? So there is only one transformation that would work, which is called affine transformation, where we see it's just some real value of constant plus a positive positive value multiplied by UC. This would also represent the same preference. And I'm not going to go through this, but because I already did that in the lecture recording. So it's just to show you that, okay, with that, you can say that when we use this affine transformation, then VC1 is also equal to A plus B times U C1 C2, where U here is the expected utility, right? Which is could be detailed like this, and then you can see that this one would also equal to that, right? Where VC1 would equal to this, so on. So next, we're gonna draw the indifference curve based on this von Neumann and Morgenstern utility function, or the expected utility function, right? Given that U, capital U, C1, C2 is equal to pi times U C1 plus 1 less pi times U C2. This is just make it very simple, only 2. In this case, when we're dealing with indifference curve, now we just assume that there are only 2 possible mutually exclusive events, not 3 or 4. Okay, that is just like how indifference curve works. Like we only make it simple, only 2 in this case. If you're gonna analyze it using an indifference curve, there are only 2 possible events. And then we can draw an indifference curve. Then we need the MRS, right? Okay, this one, remember that we have seen it before, right? You just take the partial derivative of U with respect to C1, you get that, it's MU1, and then this is MUC2. Okay, and this is always negative. You can see that it's always negative because this probability has to be between 0 and 1. Therefore, this is also between 0 and 1. And U prime is positive value, right? U prime. So what does U prime mean? U prime is the U prime C1 is the marginal utility of wells or the consumption at state 1, right? Marginal utility of the consumption at state 1. What does it mean? It means that if it's positive, that means that when there is more consumption in state 1 or more wells, higher wells in state 1, then you will be happier, right? It's U prime C1 is positive. That means when C1 increases and you have more wealth, then your total utility, right? You will be happier. It's like kind of monotone kind of thing. Yeah, think of it that way. Since this is positive, 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 all of these are positive, you multiply by negative, so this is a negative slope. So the indifference curve of this expected utility function is a downward sloping, and the slope is equal to this. You can say that it doesn't equal to that, okay? It's equal to the whole thing. All right, now the whole thing, because the utility function look like this. This is not just, these terms alone is not the slope. It could be the slope in a certain condition, which is when C1 is equal to C2. What does it mean by C1 is equal to C2? That is when it is certainty. When the wealth is certainty, that means it doesn't matter that you end up with state 1 or state 2, you will have the same wealth, right? It's along the 45-degree line. So when C1 is equal to C2, you know what happened? You see what happened? If C1 is equal to C2, then this value and this value would be the same value, right? So you can cancel each other out because C1 is equal to C2. Then you end up with this amount of the slope of the indifference curve. So regardless of what the utility function is, right? Because these two terms will always equal to one another at the 45-degree line, along the 45-degree line. So what does it tell you? What does you learn from this result? That means that if you draw the indifference curve, right? Doesn't matter. how the indifference curve look like doesn't matter the shape. You just know that any bundle, not bundle, I mean any point along this is where C1 is equal to C2, right? The slope of the indifference curve here must be equal to that. Any point here must be equal to that. But the point here or the point here not necessarily will not, most likely, almost surely that is not going to be equal to that, right? Just like, for example, at that point, I put it that point, at that point, right? What happened here at that point? You will have any of this part, any consumption in this section means C1 is greater than C2, right? Here in this part will be C1 is greater than C2. Below here, that's C2. No, sorry. C1 is smaller than C2. Oh, why would I put C1, C2 like that? Oh, it should be this. Don't make this mistake I make. So C1 should be on the horizontal axis and C2 on the vertical axis. Then now this C2 will be greater than C1, yeah. And now this C1 would be greater than C2, okay? Okay, so for this point, for example, right? That means that if we considering this point where C2 is bigger than C1, right? If C2 is bigger than C1, so this one is greater than this value. We know that this one is constant, right? But C1 and C2, if you move the point along these planes, the relative value of these two gonna change, right? U prime C1 over U prime C2 gonna change, right? Because C1 is different from C2. And now what we need to see is how the relative, how does it affect the relative change of this term between these two terms? So do we have diminishing marginal rate of substitution? What does it mean by diminishing marginal rate of substitution? Diminishing marginal rate of substitution, that means that when you, right, when you increase one consumption, right, when you increase one consumption, then it's like you will need to substitute. You will need, you are sacrificing the other good, right? So if you move, like if you move here, that means that, okay, you consume more C1, but less C2, right? As the further that you move down here, the more C1 you consume and the smaller and smaller C2 that you have. So the diminishing marginal rate of substitution says that if you increase one consumption, you actually, the reduction of the other good that you have to sacrifice will become smaller and smaller because you have so much of this good, whereas you have less and less of this good. So you would want to sacrifice less and less of C2, for example, right? And that is diminishing marginal rate of substitution. And do we have that? For this, for this expected utility function, do we have this or we don't? Remember, it's different from the utility theory. This expected utility theory. So do we have this or not? Well, it actually depends on the risk preference. Risk preference, a consumer is said to be risk averse, risk neutral, or risk loving. Risk averse, if she strictly prefers receiving the expected value of a gamble to playing the gamble. Risk neutral, indifferent between receiving the expected value of gamble or playing the gamble. Risk loving, if strictly prefer playing a gamble to receiving its expected value. In other words, a consumer is risk averse if the utility function is concave. Risk neutral if utility function is linear. Risk loving if the utility function is convex, right? So you can actually identify the risk aversion of the consumer by checking the utility function. So major aspect when you the interest curve is convex. So here, this is not the indifference curve kind of. This is, we are talking about risk averse. I'm not talking about indifference curve here. I'm talking about risk aversion and the utility function, the relationship between the risk aversion or the risk attitude of the consumer and the concavity of utility function. Or you can, so for that question is probably relevant to the indifference curve is convex like this, right? Like this. So usually when you have a convex indifference curve, okay, let me answer this question first. So you have a convex, this is an indifference curve, right? That actually this indifference curve derived based on the utility function supposed to be concave. So there is a proof to show that when utility function is concave, then you know your preference is convex. But we're not going to show to that. It's just like that. It's the identity that if utility function is concave, so that is that your utility has to be continuous, right? If you don't have a continuous utility function, then you cannot say that it's concave. But if utility function is concave, you will have so you just it's just one of the property. If utility function is concave, then the preference is convex, or the indifference curve is convex, or the preference is convex. Okay, so this is just a property that we didn't discuss this in this course because I think it's too advanced for this course. So it's just the property that if you have a concave utility function, your preference is going to be convex and the indifference curve going to be convex. But now for this, I'm not talking about indifference curve being convex or not. I'm talking about risk attitude and the concavity of the utility function. Okay. So again, we just give you the definition of or the property of this, that okay, you know what, if the consumer is risk averse, then his or her utility has to be concave, and or if her utility is concave, then we can tell straight away that her risk attitude is risk averse. So if and only if, like if you have that, you have another one, or vice versa. Okay, so for concave, you know what? How can you check the concavity of the utility function? For utility function to be concave, we know that U prime is positive, right? Because of monotone. The more wealth, the happier you are, right? And U double prime have to be negative, right? That's a concave. For linear, of course, for linear, we'll have U prime, which is a constant, right? And U double prime is 0. Right, just a linear. For the convex, U prime is positive, right? And U double prime will also be positive. That's a convex. So very easy. If I ask you, can you tell me if this person risk averse, risk neutral, or risk loving? If you know utility function, how do you do it? You just check U prime and U double prime. That's it, right? And you don't need to check the partial derivative, because here in this expected utility function, there is only one variable, which is wealth or the consumption. That's it, not x and y, only one value. So only one variable. So you check U prime, the bill is positive. So apparently it has to be positive, and you just need to check, verify the U double prime. If it's negative, then it is concave. That means that the consumer is risk averse. If it stays positive, then that means that this consumer is risk loving. If it's a linear, if utility function is linear, then it's risk neutral. Okay, like this. it's very clear that this is concave utility function, right? This utility function is concave, so this consumer is risk averse. So I think majority of the students may have a hard time to actually understand this diagram or this illustration. So since we are dealing with this uncertainty, right? And we're looking at, let's say that we are having only two possible outcomes, two possible events, right? Low event or high event. So if we get high event, this is the high wealth that we would obtain. If we get the low event, this is going to be the wealth or the outcome associated to that low event. Okay. And this is a utility that is assigned across the wealth. Okay. Which is concave, right? So if I want to compute the expected wealth, right? And I say, okay, expected wealth has to be equal to P times WL, right? This is P times W. You don't need utility function here, or P1 or P, just V, because there are only two events, plus 1 less P times WH, right? This P is the probability that we get low outcome, and the other event is the other probability is when we get a high outcome. Okay, so where is this value is located on this diagram? You see that this is actually similar to the convex combination, the convex value that we learned when we were talking about what is it? We are talking about the not continuous. Is it like, what is it? That property? Now I forgot. That not worse than convex, right? When we talk about a convex preference, remember? And then we check that and it's one of the problem set, one question, that check whether or not the preference is convex. Then you need to pick two bundles, right? Two bundles, right? The two extreme bundle, and check that the average, the bundle in the average had to be not worse than, the extreme, right? So, and this is basically your convex combination, but instead of dealing with X and Y, now you're dealing with only one variable instead of two dimensions, just one dimension, W. So this P and 1 minus P, right? So it's like an average. So the expected value is like an average. So this P could be 1/2, or could be, any other values between 0 and 1, right? So if this is the WL, the WH, then EW, which is your convex combination between the WL and the WH, has to be somewhere along here, right? Which is here. So if P is equal to this, 1 minus P is that, then this is going to be the amount of EW. So this is EW. Okay. Right. Now with this EW, okay, if I go up to here, what is this value? That is, if I give you somewhere in between the WL and the WH, that is the utility value of my expected wealth. Okay, so I'm gonna put it up here. Right, it is utility, actually is a utility. This utility of the expected wealth. Okay, so this is that point there, because it's on. It's like, let's say that if this one is, can I give you some random number? This one is 2, this one at 10, and this one is, let's say 3, for example. Like the expected wealth is equal to 3, right? Then this value here. So if I plug 3 into my utility function, let's say my utility function is equal to log W, right? So I can plug this equal to log 3, and that is what I'm getting here. This is my U of 3, right? This is U of 3. It's going to be my U of 3 or U of EW. Okay. So what can I say? U of EW was equal to log of EW, which is equal to log 3. For example, just give you some, some fixed values to work with, so you have a better idea than just a notation. Okay, so that would be, and you can see that this is concave utility function because, right, the utility of the expected wealth is actually higher than the expected utility. So this is the expected utility value, right? EUW, expected utility. So this one, EUW is actually what equal to P times UWL, right? Plus 1 less P times UWH. This is the expected utility. See, it's different, right? The main difference is this. Okay, that is the difference. So this one, right, is actually this. So if this is a risk-averse person because utility function is concave. Okay, so the interpretation is if this person were given the sure money of the expected value of wealth, right? If this person is given this sure money $3, her utility of this sure money would be greater than the expected utility, right? So that means she would prefer this to that, right? Because this one is higher than that. So she would prefer the sure thing over the uncertain option because this is uncertain. And how do we know that this is actually equal to that, right? So this point, this height here is equal to expected utility value. Well, remember, expected utility value consists of two parts, PUWL plus the second part, 1 minus P times UWH, right? So let's start look at the UWL first. UWL, this is the WL. Therefore, UWL has to be, this is UWL, right? Has to be this much. UWH has to be this much. Okay. So I'm gonna just erase this one a moment. So this is UWL. This one is UWH, right? So, and now if you look at this, guess what? Convex combination between UWH and UWL, right? You look at the convex combination, you go through here, right? This is your convex combination right there. Like PUWL. So that is the point where, so if you draw this this line like this, right? So that would be exactly, oh no, sorry, that would be exactly like a convex. So you have 2 points, right? You have UWL here and UWH here. You draw a straight line. The convex combination between these 2 points is your expected utility value. So it has to be a straight line. See, you draw a straight line here or a straight line there, right? So it's gonna be there, it's gonna be here. That point, not that point, sorry. It has to be this point, okay? Okay, so because of the concave utility function, so this consumer would prefer this U of the sure thing over the uncertain option, right? finding the certainty equivalent. So, okay, what would be the certainty equivalent? That means that now this is my expected utility, right? I know this is the amount of expected utility given this, this option. So how much do I need in order to be, indifferent between gamble and obtain this much of expected utility versus receive the sure thing? To receive the sure thing, I need this amount of certainty equivalent. If I get this much amount of certainty equivalent, right, you can say that my utility, the utility of my CE is equal to expected utility value. So that's how I could find what this CE is. So basically you just set up this equality. So if you know, you can compute this, you could compute this, right? Expected utility value, you can compute this. And if you, of course, you need to know utility function, and you find what is the certainty certainty equivalent is, right? And that you actually have already done that in this one, in this exercise that we did. This one, you have already done that. Did you notice that? This is a certainty equivalent. So the certainty equivalent is this is what you need, right? You need this much amount to be indifferent between this uncertain versus the certain. So that is the amount that you need, right? So this is so pretty much this is a certainty equivalent. If I just put the equal sign here, okay, that's going to be the certainty equivalent. When expected utility in option B, because B is now a sure thing, right? You have a sure thing, only one possible event. So this is your sure certainty equivalent that make you indifferent between risky option versus non-risky option. So the certainty equivalent. So I call this one, this part, right? This CE, certainty equivalent. All right. So, okay, I have about 20 minutes to talk about the insurance. Okay, so far, everyone's still okay until here. Then we have talked about the MRS, which is negative pi over 1 minus pi times u prime C1 over u prime C2, right? That is a slope. And we also learn about the risk attitude. Now I'm gonna take it further to the application of insurance, right? So insurance, there are two possible scenarios. It's an accident or you don't have accident, right? And this is 45-degree line. That means that it's gonna be the certainty wealth, regardless you have accident or not, you will end up with the same wealth. Doesn't matter, right? So with the insurance, you know that with insurance, right, you can, if you end up with the accident, you will lose the wealth by the amount of the loss that caused by an accident. So you just start from the bill, right? Then with an accident, you lost by this much. Remember, we're gonna move to this direction because that is the direction of the amount of wealth in the case of accident, right? So if you have an accident, your wealth will be reduced. So the wealth of the accident, the wealth of the accident would be the first element. The wealth of the accident will be reduced by the bill, by L. And what about no accident? Then you stay at the bill, right? Without accident, then you get the bill. So still stay at the bill, but less wealth in the case of accident. So you stay at point E, right? At that point E, this is what you will have. Point E, you either could have the wealth, the same wealth, or the wealth less the loss of the accident. And then we know that that is going to be the affordable point for you, right? It must belong to your budget set, right? Because you can, do the point is must be affordable, so you may end up with this or end up with that. Now that you're thinking about whether or not you should buy an insurance, right? Let's say the insurance costs you P dollars per unit of insurance, so you can buy as many insurance that you want, but each unit of insurance costs you P dollars, and let's say that P dollar is between 0 and 1. Okay. So with that, if you want to move from point E, which is no insurance, right? If no insurance, you might end up with this wealth or that wealth. Or you can purchase insurance. If you purchase the insurance, what is going to happen? If you purchase the insurance, that means that if you do not have accident, what happened to your wealth when you purchase? Let's say you purchase 1 unit of insurance. That means that your wealth will be reduced by the bill less P, right? Here, right? Because you have to pay the insurance for 1 unit. So you end up with here. It's going to be the bill less P, right? But if you do have an accident, given that you buy insurance, what is the wealth in the case of accident, given that you buy insurance? Then the wealth in the accident would be, yes, you will have the bill minus L and minus P, because you paid for the insurance, right? So that is, but you will be paid back by, one unit, because you buy 1 unit of insurance. That means that in the case of accident, then you can claim for that 1 unit that you purchase of the price P, right? So when you buy insurance, this is going to happen. So you have the bill less P plus 1, right? So you're actually going to be increased by 1 less P, right? So you reduce by P, and then the wealth in the case of accident should increase by this amount, given that P is between 0 and 1. Okay, so that means that this number is going to be positive. So you move to this side. So this is going to be the bill minus L minus P minus 1. Okay. Bill minus P minus L minus P, because you buy insurance, plus insurance payout. Okay. So these 2 points, these 2 bundles must be on the same budget line, because that means that these are affordable, right? You choose not to purchase insurance, or you choose to purchase 1 unit of insurance. What about you purchase 2 units of insurance? You purchase 2 units of insurance, then that means that this one gonna decrease by 2P, right? And then this gonna be increased by 1, 2 times 1 minus P, right? Because if you buy 2 units of insurance, that means that you have to pay 2 times P. But in the case of payout, you will be paid 2 because you buy 2 units. And if you do not have accident, but you buy 2 units of insurance, then you end up with the bill less 2P, right? Because you pay 2 units of insurance. So the new affordable, the new bundle would be here, right? So the more units of insurance that you buy, you're actually going to move down along the curve, right? gonna be moving down, but it's gonna be on the same slope. So the slope is the same. You can see that it doesn't matter. Your slope is gonna be the ratio of p over 1 minus p anyway. So either this or this or this over this, doesn't matter. It's gonna be a constant rate still. So that's gonna be like this, like a straight line, just like a budget line that you are familiar with. But the slope of the budget line, instead of like px over py, now it's gonna be the price of insurance instead, or p over 1 minus p instead of px over py. Okay, so as you increase more units of insurance that you buy, then you're gonna be moving downward over further out, further down, right? Okay, so now you understand the slope of the budget line. So we know that with this, the slope of the budget line in the case of insurance purchase is p divided by 1 minus p. Okay, that's a slope, negative, of course, right? That's the point E, any point, depending on how many units of insurance you buy. Okay, we have 45-degree line that represents C1 equal to C2. And what we need, we want to find the optimal bundle for this consumer that maximize the expected utility value, right? Because of this uncertainty. So we have, let's say, indifference curve look like that. So this indifference curve is more like a indifference curve of the expected utility function, right? Utility function, expected utility function is pi UC1 plus 1 less pi UC2. Okay. Just move here a little bit. Okay, move it a little bit here. All right. So this indifference curve is derived based on this. So since it takes this shape, look like this shape, because if we assume that the utility function is concave, it's gonna look something like this. And we also learned that along the 45-degree lines, right? The slope of this indifference curve or the MRS has to be equal to that. Remember, when C1 is equal to C2, then that is the MRS. Okay. Insurance is actually fair if the insurance premium is the expected value of the insurance. So when P is equal to pi, right? P is the premium, the price of the insurance is equal to the expected value of the insurance. So this is expected value of insurance is insurance premium. So when P is equal to pi, that is actually fair, right? So you can think about it. That pi is the probability that the accident occurs, right? Where P is the premium between 0 and 1. So if the price is actually equals to the probability that the accident occurs, then you think this is a fair insurance premium. And in that case, that means that the slope of the budget line, right? Remember the slope of the budget line is this. Right? It's the slope, the budget line slope is equal to this, right? If P is equal to pi, then that means that the slope of the budget line is equal to that. And what is that? That is the slope of the indifference curve along the 45-degree line, right? That would be exactly. So if you draw the indifference curve, this is going to be tangent to your indifference curve, right? Because the slope of the budget line is equal to the MRS, because P is equal to pi. So the optimal solution, So what is going to happen here is this consumer will just buy the insurance such that C1 and C2 are the same. What does that mean? Right? This is gonna be what she's gonna buy. The amount of insurance, it doesn't matter what amount of insurance she buy, but she would buy in such a way that in the case it's accident happens or not, she will end up with the same amount of wealth because it is 45 lira. Implication, that means she would buy the units of insurance such that it fully cover her loss, right? So if she doesn't buy insurance, she stay at E, but then she's gonna choose that point. To get to that point, that means she had to buy the unit of insurance such that, you know, accident or no accident, she end up with the same wealth. So she pay, this one would be equal to, right? This one gonna be equal to W minus, I call it P times X. X is a unit of insurance, right? And the second will be W less L less 1 minus plus 1 less P times X. Okay, right? And for these two numbers to be exactly the same, right? So these two numbers to be exactly the same, that means that we have W minus PX plus X less L, right? This is equal to that. So for this to be equal to that, that means the only possibility is X must be equal to L, or this consumer will purchase the unit of insurance that is exactly equal to the loss, or she would be fully insured, right? So this term has to be 0, right? So that this one is equal to that. That is the point. So when purchasing fair insurance, you see that MRS is equal to the budget law, then she will choose this, and that means that implies that X must be equal to L. Okay, W minus pi L, W minus pi L. So X must be equal to L, fully insured. Okay. What if the insurance is unfair in favor of the insurance company? So instead, before it said, okay, if P equal to pi, this is what the result you're gonna see, given that the consumer is, you know, is risk averse or not. Actually, it doesn't. Yeah, it doesn't actually. It doesn't depend on the utility function at all, right? The result here doesn't depend on utility function, because it doesn't matter what utility function is. We just know that anything along this point, right? The slope is pi over 1 minus pi. So it doesn't matter of the utility function. So if it doesn't matter the utility function, it doesn't matter of what the risk attitude the consumer has. Right? As long as P is equal to pi, then the solution is going to be there, which means all three types of risk attitude consumers will choose to fully insure. Now, what happens if insurance is actually unfair, whereas the insurance premium actually is more expensive, or it's greater than the probability that the accident happens, right? This is actually more interesting. What is going to happen? Will the consumer underinsure, choose X less than L, overinsure, or fully insure? I will show you in the case where P is smaller than pi. So when the in insurance actually is cheaper, right? You would expect, like in the common sense. So if you have to pay less than the chance that you will get the accident and will get the payout, then you would say, okay, then I will buy it, right? Actually, I would actually buy more. And that was your intuition, and you could actually try to explain using this setup. When p is less than pi, right? So when p is less than pi, so that means your MRS, which is negative pi over 1 minus pi. Don't forget that actually you need to have this as well, right? This is the MRS, not just this. It's the whole thing. MRS equal to this term only when we are along the 45-degree line, okay? And the slope of the indifference curve, budget line slope, is equal to negative p over 1 minus p, right? Now that if you just compare with the p 1 minus p between pi 1 minus pi, if p is smaller than pi, right? That means that this is going to happen. So the budget line slope is actually greater than that value. So that means it's going to be something like this, right? Something like this, not like that. It's going to be something like this. Then the tangency condition, MRS has to be equal to the slope of the budget line. Remember MRS now. So you know that if it's not equal, then we're not going to have this. So we're not going to have this result. But instead, what you are going to have is the slope of the budget line in the tangency condition. With the tangency condition, you need to have p over 1 minus p is equal to pi over 1 minus pi times u prime c1 over u prime c2, right? Guess what? You have information about these two terms. You know that this one is smaller than that. For these two terms to be equal, what does it mean? That means that this term has to be small, right? Given that this one is smaller than that, so this one is greater. So for these two terms to be equal, this one has to be small, right? For this term to be small, that means this one has to be large and this term has to be small, right? U prime C one has to be greater, no, sorry, has to be smaller than U prime C2. Right? This one is smaller than that. That means this one has to be small. Okay, we need this one to be small. To be small, that means this one should be small and this one should be big. And how can we say that this one is big and this one is small? Depends on whether or not you are risk averse or risk neutral or risk loving, right? So if you are risk averse, that means that C2 has to be quite small and C1 has to be large for this to hold, right? Because when you are risk averse, then that means that the MRS will get smaller and smaller with the large value, right? For risk averse, the bigger the value of C, the smaller the MRS. For the risk neutral, doesn't matter the size of C1, the size of C, the marginal rate, the MU is stay the same because it's linear. Whereas a risk loving, right? The risk loving, the higher the value of C or the higher the value of wealth, the higher the marginal utility of that wealth. So it all depends on the risk attitude here, right? If you are risk averse, let's say if you're risk averse, then what that means is that for this condition to hold, C2 has to be actually small, right? If C2 is small, the U prime C2 will be large and C1 has to be large. So this one has to be, C1 has to be large. So C1 itself has to be large and C2 itself has to be small, right? So C2 has to be smaller than C1. This is C1. This is C2. So C2 has to be smaller than C1. So it has to be somewhere here. So you can actually predict where is the optimal amount of insurance that this risk-averse person is going to buy, right? So he's gonna choose to buy somewhere here, because here is where C2 is small, right? C2 is smaller than C1, so somewhere here. And what happened is the point here. The point here is when you actually buy more than the loss, so you over-insure. So any point along here, X is greater than L. This point, X equal to L. So any point here, X is equal to L. Any point up here, X is smaller than L. So fully insure along here. Any bundle here on this side, you over insure. Any bundles here, any point along here, you what is that? You under insure. Under insure. If choose somewhere here, under insure. Choose somewhere here, over insure. Anything along here, fully insure. Just insure exactly where how much the loss is. Okay, so I finished exactly at 4 p.m. and this insurance thing is is an application that could be a bit complicated and challenging. So if you don't get it for the first time, like when I'm talking during my talk, and that's completely normal. You can, you can try to think of it at your own time and really try to understand what that is. I think the main thing is you need to compare between, so let's go it one layer by one layer. Just compare the slope of the budget line versus the slope of the indifference curve. Okay, and then just like started to try to see the relationship of what is going to happen and what should be the optimal bundle or optimal point, and where it once you start to find you kind of find the relative relation between C1 and C2, then you can, oh, okay, if it's go here, then that means this person will under insure. If it's somewhere here, then they're going to be over insure. And also it depends on, right, on the risk attitude of the consumer. Okay, so anyone have any questions? And I will post more detailed information about the problem set to, sometimes maybe by Friday. And so to give you some ideas of what to focus on. And again, if you don't get some concept, like out of the concept right today, you can always go back and listen to the listen and watch the video later. Okay, any questions? No question? Okay. Then, oh, by the way, we don't have a Q&A next week. Okay, so this is gonna be the last Q&A before the problem set. So just another thing that I forgot to mention. I will make an announcement again also by Friday. Okay, bye-bye. See you later. Bye.